In this video, we're going to talk about the general binomial expansion. In year 12, we discovered this result. But remember that this result was only true when n was a positive integer. So the aim of this is to find a more general result that holds true when n is not a positive integer. So n could be negative, or n could be fractional, or n could even be something irrational like pi. So to start with, I want to consider a more particular expansion, and I want to consider the expansion of 1 plus x to the power of n. I'm still considering n to be a positive integer here. So this is n choose 0. Well, this is just like the previous one, but we have a equals 1 and b equals x. So a to the power of n is 1 plus n choose 1 x plus n choose 2 x squared, all the way up to our final term of n choose n x to the power of n. And now I want to think about these binomial coefficients, which are our n choose r. And you may have used Pascal's triangle to find these, or you may have used the formula n choose r is equal to n factorial over r factorial n minus r factorial. And let's go and calculate a few of these. So I think we already know that n choose 0 is equal to 1, but we can show that using the formula. So n choose 0 is equal to n factorial over 0 factorial n factorial. Well, that is, the n factorials cancel and 0 factorial is 1, so that is 1. What about n choose 1? Well, n choose 1 is equal to n factorial over 1 factorial n minus 1 factorial. Well, that is n multiplied by n minus 1 multiplied by n minus 2, all the way down to times 1. 1 factorial is 1, so this is divided by n minus 1 times n minus 2. So we can see that all these factors cancel. So n choose 1 is just equal to n. Okay, what about n choose 2? Well, n choose 2 is equal to n factorial, so n minus 1, n minus 2, all the way down to 1, divided by 2 factorial, and then n minus 2 factorial, so n minus 2, n minus 3, all the way down to 1. Well, we can see that the n minus 2 factor cancels, n minus 3 cancels, so we are left with n multiplied by n minus 1 all over 2 factorial. Now let's consider n choose 3. Well, n choose 3 is equal to n minus 1, n minus 2, n minus 3, etc. divided by 3 factorial, n minus 3 factorial, which is n minus 3, n minus 4. So all of these factors on the denominator, the n minus 3, the n minus 4, cancel with a factor on the numerator. So we end up with n minus 1, n minus 2 over 3 factorial. And in general, what do we think n choose 4 might be? Well, we can perhaps see that what we're going to end up with here is n minus 1, n minus 2, n minus 3 over 4 factorial. And in general, for n choose r, we're going to get n minus 1, n minus 2, all the way to n minus r plus 1 over r factorial. So what can we say? And all I'm going to do is write out this result here in a slightly different way. We can say that 1 plus x to the n, and we're still thinking about positive integer n, is equal to 1 plus n choose 1, which was n, lots of x, plus n choose 2, which is n minus 1 over 2 factorial, lots of x squared, plus n minus 1, n minus 2 over 3 factorial, lots of x cubed, all the way to x to the n. Okay, so this result here is true when n is a positive integer. And my claim is that a very similar result holds when n is negative and or it is a non-integer. So I'm going to claim that 1 plus x to the n is equal to 1 plus nx plus n minus 1 over 2 factorial x squared plus n minus 1 n minus 2 over 3 factorial x cubed plus dot 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 plus n minus 1 dot 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 n minus r plus 1 over r factorial x to the power of r plus some more terms. Well, this result holds for all real values of n. And there's an important difference here, because this expression here, expansion, but this has an infinite number of terms, so this is an infinite expansion. And that is the important difference here. And I'm not going to prove that this result works. That's something that's beyond our A-level studies, but if you do further maths, you'll come on and you will study Maclaurin expansions and you will prove this result. So this result here is our general binomial expansion for all values of n. And it's just worth noting that if n is a positive integer, then for r greater than n, the coefficients are equal to 0. And so the expansion terminates. And to see that, realise that if n is a positive integer, at some point, if you're doing n times n minus 1 times n minus 2, etc., at some point when you get to large values of r, you can get all the way to times 0. And that means that any expressions after these large values of r are always going to be equal to 0. So you're just going to get this same result as this. However, if n is not a positive integer, then all coefficients are non-zero. And to see that, realise what you're doing is you're doing n minus 1, then n minus 2, then n minus 3, then n minus 4, etc. So you're always subtracting an integer from n. So if n is not an integer, none of these factors are ever going to be 0. So all of these coefficients are going to be non-zero. So that means when n is not a positive integer, this expansion is an infinite expansion. So now I'd like to do an example to show how we might use this expansion to expand something like 1 over 1 minus 2x all squared. And to start this, we need to get it to look a little bit like this. Well, we know that this is equal to 1 minus 2x to the power of negative 2. So that's a lot better because we can see that now we have n is negative 2. And we're told that this is true for all real n, so n is negative 2 is absolutely fine. But we also need to be a little bit careful because our general result has a positive x here, yet we're dealing with a negative 2x. So when we use this result, in the place of all of our x's, we're going to have to write negative 2x. So let's go ahead and do this. What do we get? Well, we get equals to 1, and then we have nx, which is negative 2, times by negative x, but it's not x, it's negative 2x, so multiplied by negative 2x. Then we have negative n times n minus 1, so negative 2 and negative 3, divided by 2 factorial, multiplied by x squared, so negative 2x squared, and those brackets are important. And then the next term is going to be n, which is negative 2, multiplied by negative 3, multiplied by negative 4, over 3 factorial, multiplied by negative 2x all cubed. And if you were given this question in a textbook or an exam or something, they'd probably tell you how many terms they want. I'm going to stop at this term here, but please pay careful attention to that. I can put this ... to show that I know there are lots more terms. In fact, there's an infinite number of terms here. So now I'm just going to simplify this. So we get 1, and then we have negative 2 times negative 2, which is positive 4. So positive 4x. And then here we have minus 2 times minus 3. So we have, that is going to be 2 times 3 over 2 factorial. And then negative 2x squared is going to be 4x squared. Well, this factor of 2 cancels, so actually it is 3 times 4x squared. What do we have here? Well, we have negative times negative times negative, but then also we have negative 2x cubed, so that's 6 negatives being multiplied together, so it's positive. So 2 times 3 times 4 over 3 factorial, so 3 times 2 times by 8, and we don't need to write negative x here because we've accounted for it in our signs, 8x cubed plus our remaining terms. And we can see here that the 3 times 2 cancels with the 3 times 2 here, so we have 4 times 8. So what is this equal to? It's equal to 1 plus 4x plus 3 times 4, which is 12x squared, plus 4 times 8, which is 32x cubed, plus these remaining terms here. So we can say 1 over 1 minus 2x all squared is equal to 1 plus 4x plus 12x squared plus 32x cubed plus some plus our remaining terms that we've not calculated. But we can also say something like this. We can say 1 over 1 minus 2x squared is approximately equal to 1 plus 4x plus 12x squared plus 32x cubed. And I don't need the ... here because I'm saying they're approximately equal to. And a sensible question you might be asking here is this always true? Is this always true? And if not, for which values of x is it true? And to see this, we can consider the graph of 1 over 1 minus 2x all squared. So in blue here we have the graph of y equals 1 over 1 minus 2x all squared. In orange we have the binomial expansion up to the power up to x to the power of n. And at the moment x equals 1, so we have 1 plus 4x, which is the first two terms of the expansion we found. And if I start to change this x, if I change to x equals 2 to n equals 2, we can see that we have 1 plus 4x plus 12x squared. And we can see that the orange graph is a much better approximation to the blue graph when n equals 2. But it's only a good approximation in a very small area. So it's only a good approximation when x is close to 0. When x is like 1.2, the orange and the blue graph are way out. And similarly, when we take these negative x, for example, x is negative 1, the blue and the orange graphs have considerably different y values. So we can see that actually it's close to 0 is when the approximation is a good one. If we go to n equals 3, which is what we calculated before, well, we can see that's a lot better when we have those small values of x. But once we start getting away from x equals 0, the approximation is pretty rubbish. So the answer to when is the approximation good is really that for small values of x, it's a very good approximation, but for large values of x, it isn't at all. But what about if we take the infinite expansion, so take all of the terms? Well, let's increase our number of terms here, and we can see that as n increases, that approximation gets better and better and better. And when we get as far as n equals 12, it's actually not too bad at all. It's really pretty good, but only in this middle part. So the infinite expansion, and this is only to 12 terms, but if we took the infinite number of terms, between a certain values, the orange and blue curves are going to coincide, but it is absolutely not going to be equal in this branch, for example. So it might be clear to you, and a proof of why this is the case is beyond your A-level course, but as n increases, it gets closer and closer and closer when x is between minus a half and plus a half. And in the infinite expansion, the expansions are exactly equal between x is minus a half and a half. But when x is outside of that, the expansion is not valid at all when x is not between negative a half and a half. So what we can say is that this is a good approximation for small x, but this statement here, that 1 over 1 minus 2x all squared is exactly equal to 1 plus 4x plus 12x squared plus 32x cubed plus all of these remaining terms, well, that is only valid when x is between negative a half and a half. And if we go back to our original expansion here and ask when is this valid, well, in general, this is valid when x is between negative 1 and 1. And we can see that this gives us the same result as we had before, because then that means this expansion will be valid when negative 2x is between negative 1 and 1, which is equivalent to saying x is between negative a half and a half. And we can perhaps get an idea of what's going on here by considering some examples and substituting some values of x in. So let's take, for example, x equal to 1. Then we know that the left-hand side, which is 1 over 1 minus 2x all squared, is equal to 1 over 1 minus 2x, well, that's negative 1 squared, which is then equal to 1. Well, the right-hand side, which is 1 plus 4x plus 12x squared, is going to be equal to 1 plus 4 plus 12 plus 32 plus adding on increasingly large numbers. Well, this is clearly not equal to 1. And what this is what we might call a divergent series. And you're going to learn a bit more about divergent series when you do sequences and series. But it's clearly not the case that this is true when x equals 1. So this is not true when x equals 1. But let's take something that is between negative a half and a half. So let's take x is equal to a quarter. And then the left-hand side is equal to 1 over 1. 2 times a quarter is a half, so 1 minus a half is a half, so 1 over a half squared, which is equal to 4. And then the right-hand side is going to be equal to 1 plus 4 times a quarter plus 12 times a quarter squared plus 32 times a quarter cubed plus these plus all these infinite terms. Well, what do we get? We get 1 plus 1 plus 12 over 16 is 3 quarters plus 32 over 64 is a half plus these remaining terms here. Well, we can see that this is 3 and a quarter plus some remaining terms here. Well, notice this isn't equal to this isn't equal to 4, but I'm not going to prove this now. But if we continue calculating these remaining terms, the more terms we calculate, the closer this will get to 4. So this is a series that converges, and in particular, it converges to 4, which is what we wanted. So it is true. This statement here is true when x equals a quarter.